Humanity is pushing deeper into space than ever before. We're talking thousands of new satellites, big plans for the moon, even Mars. But every single one of those missions, every satellite, every station, every future colony, it all hinges on one single critical thing: power. So, how do we solve this massive energy problem out there in the final frontier? Let's get into it.
I mean, to really get the scale of this, just look at the International Space Station. Its solar arrays are absolutely massive, spanning about the size of a football field. And they're covered in more than 250,000 traditional silicon solar cells. Yeah, they're powerful, but they are also incredibly heavy and totally rigid.
And here's the thing about space. Weight is everything. Right now, it costs about $4,000 to launch a single kilogram, that's just over 2 pounds, into orbit. Think about that. That's like paying for a decent used car just to send up a small bag of flour. That cost is a huge, huge roadblock to doing more in space.
So this brings us to the big question, right? You've got companies planning these mega constellations with literally tens of thousands of new satellites. How on earth do we power all of them without completely breaking the bank? The old way, with those heavy panels, is just not going to cut it. It's too heavy, it's too expensive. We need something completely new.
And that's something new? Well, it might just be a technology called the organic solar cell. We'll call it an OSC for short. This is a totally different way of thinking about solar power. Instead of silicon, it uses carbon-based materials, and it has the potential to completely flip the script on how we power things in space. Just look at the difference here. I mean, it's night and day. Unlike those bulky, stiff panels we're all used to, organic solar cells can be made paper-thin, super flexible, and you can even make them semi-transparent. Honestly, they look and feel more like a sheet of plastic wrap than a solar panel. It's wild.
So these unique features give OSCs some serious superpowers for space. First off, they're ultra-lightweight and flexible. They can even be made using low-cost methods that are kind of like printing. But their real secret weapon is something called specific power. All that means is you get more power for less weight. And since every single kilogram costs a fortune to launch, getting more watts per kilo, well, that's the holy grail for space tech.
So how does this whole thing work? Well, you can think of it like a 4-step dance. First, a photon of light hits the cell and creates something called an exciton, which is basically just a little energy packet. Then, this exciton zips over to a special layer inside. Think of it like a sorting facility, where it gets split apart into an electron and a hole. From there, the electrons and holes go their separate ways down different paths. And finally, they're collected at the electrodes. And bam, that creates an electrical current.
Okay, so being light and efficient is awesome, but that's not enough, not even close. To actually make it in orbit, this new tech has to survive one of the most brutal, unforgiving environments you can possibly imagine. It has to run what you might call the cosmic gauntlet. And the villains in this story? They are relentless. You've got the Van Allen belts, which are full of trapped, high-energy particles. You've got insane temperature swings. We're talking going from -100 to +100 degrees Celsius every 90 minutes. There's a constant blast of solar wind, and then there's the vacuum of space itself, which can literally make materials just fall apart. But out of all those threats, there's one that stands out as the main bad guy, especially for solar cells in low Earth orbit, and that is proton radiation. These tiny, high-energy particles just slam into the solar cell's material over and over, creating these little defects that act like traps for electricity, killing the cell's performance over time.
So, could these promising organic solar cells actually survive all that? Well, this is where the amazing research of Dr. Gulnor Okhtanova comes into the picture. To find out, she decided to bring the brutal conditions of space right down into her lab.
What her team did was they basically blasted different kinds of organic solar cells with a beam of protons. They simulated the total dose of radiation a satellite would get after spending about 3 years in low Earth orbit. The whole point was to see which designs could take the punishment and which would fail.
The first test was all about thickness. They wanted to know, does a thinner or a thicker light-absorbing layer hold up better? And the results were super clear. The thicker cells got torn up by the proton barrage and degraded way faster. But the ultra-thin ones, they were much, much more resilient to the damage.
All right, for the second test, they compared 2 different ways of building the cells, what they call conventional and inverted. You can think of it like changing the order of the layers in a sandwich. The big difference is that the inverted design uses tougher, more robust, inorganic materials for some layers, instead of the more delicate organic ones, to see if that makes the whole cell more durable.
So after all this testing, what did they find? Well, the results were a huge deal. They basically gave us a clear blueprint for how to build a space-ready organic solar cell. These were some real breakthroughs.
Just look at this chart. The results are,
Well, they're not subtle. After getting blasted with all that radiation, the thinner cell, that's the higher bar there, kept way more of its original power. The thicker cell degraded a whole lot more. The data couldn't be clearer. When it comes to surviving radiation, thinner is definitely the winner.
And in the showdown between the two different structures, the inverted design was the undisputed champion. It turns out those tough inorganic layers were simply way better at resisting radiation damage than the organic ones used in the conventional design.
And hey, you don't have to take my word for it. Dr. Akhtonova's own thesis abstract sums it up perfectly. She wrote, "The irradiated OSC with a thin photoactive layer shows higher resilience to proton irradiation and better recovery. This research is the proof. It's the critical evidence that not only can these cells survive in space, but we now know exactly how to build them to last."
So here's the bottom line. Thanks to this incredible research, the idea of a solar cell that's not only ultra-lightweight, flexible, and cheap to make, but is also tough enough for space, well, that's not science fiction anymore. It's moving from theory into reality. And that just leaves you with one final, massive question. If we can perfect this tech for the thousands of satellites zipping around Earth, what's next? Could these lightweight, easy-to-deploy solar blankets one day be unrolled across the surface of the Moon or Mars, powering our first real human outposts in the final frontier?